Hello everyone. In this video we're going to take a look at some of the sequence types that are available inside of Python. More specifically, we're going to look at the tuple, list, and string types. I'm going to jot these down real quick just so we have an overall reference as we progress through this lesson. So once again, this is the tuple, list, and string types. Now, of course, we've seen strings before and how they can hold text, but this video is going to focus on how they are also accessible in a sequence manner. Now, what are we talking about in general when we talk about sequences? Well, you could say that a sequence object is simply an object that references 0, 1, or more other objects. Now, I think this is best explained by seeing a sequence type in action, so let us jump directly into the interactive interpreter, and let's first take a look at the immutable sequence type, that is, the tuple. The way one defines a tuple is by specifying a list of objects, comma separated using parentheses. For example, if we wanted to make the variable a tuple type, and set it to hold a sequence of the numbers 1, 2, and 3, we could say that a would be equal to opening parenthesis 1, comma 2, comma 3, and then specify a closing parenthesis. So if we execute that statement and then look at a, we can see that a is enclosed in parentheses and has the values 1, 2, and 3 in it. To get more specific, we could actually check the type of a at this point and see that it is indeed a tuple. So what we have just done here is we have made 3 objects, 3 integer instances, 1, 2, and 3. We've stored all of those into a tuple sequence, which we reference by a. Now, another thing that's interesting here is this really is just a set of object references, and that means that those individual objects could themselves be different. So in essence, we can put lots of different types into the same sequence. We could redefine our a tuple by containing the numbers 1, 2.25, a float, and the word cat, a string. And this accepts just fine. If we look into a, we can see that it now contains the objects 1, 2.25, and cat. So, very simple, but rather useful, as you'll see here shortly. Now, what are some of the things that we can do with this idea of having lots of stuff all in one container? Well, first is we can begin to analyze this in interesting ways. Let's first take a look at the built-in len function. This allows us to get the length of another object, should length be supported on it. And this in the case of strings and other sequence types, we can see how many elements or objects they contain. In the case of a, how many do we have? Well, we have 1, 2, and 3. So if we check the length of a, we should say, okay, well, 3 elements. So the len of a does indeed equal 3. We can tell that we have 3 elements inside of a. Now I wanted to go ahead and show that, the idea of getting the length of a sequence, because I wanted to give a few interesting cases when creating tuples. So far we've just seen creating a tuple with 3 elements, and that was simple enough because we would just say element, 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 and so on, comma separated. But what if we run into a case where we would want 0 or 1 elements? As the definition gets a little bit more interesting. 0 is fairly easy in that we know we were closing in parentheses, so saying a equals open closing parenthesis. This by itself will indeed create a tuple. We can look at it, we can even look at the type. Type of a is still a tuple. But what's interesting here is, well, what's interesting about this tuple? Well, let's get the length of it. Length of a is now 0. So empty parentheses are how we would go about creating a tuple sequence that had no elements in it. Now the other interesting setup is, what if we wanted to make a tuple that had only 1 element? And this is interesting because it might not seem like a problem at first, because the first thing that would seem to come to mind would be open parenthesis, the 1 element that we want, followed by a closing parenthesis. If we do this, note what happens. We look at a is not enclosed in parentheses, and if we look at the type of a, it's an integer. So what has happened is parentheses in this case are just acting like being closures to an expression. So similar to 2 plus 2 in parentheses gives 4. 1 in parentheses simply mathematically resolves 1 to 1. Now that's interesting. Now, we know we need to use a parentheses to get the tuple, so how do we get a tuple with only one element in it? Well, we can do this by specifying 1 and a trailing comma. If you have only one element, you need to specify a trailing comma so that the interpreter, so that Python knows to say, this should be treated as a tuple. Now if we look at A, it is surrounded by parentheses, and if we check its type, A is indeed a tuple. And one last thing that's interesting to point out is the fact that parentheses are not always required with tuples. If one were to say, or just give a comma-delimited list of objects, that does indeed become a tuple also. The idea here is that if we see a comma-separated list of things and there's nothing else to indicate that it is any other type, then it basically defaults to being a tuple. Now, of course, there's still scenarios where we'd have to include the comma or empty parentheses if you wanted a specific 0 element or 1 element tuple. But just keep that in mind, that if you ever run into a case or see a piece of code that has a bunch of simply comma-delimited values with no parentheses, that does indeed end up becoming a tuple. Alright, now that we've looked at how we can get a basic immutable sequence up and running and how we can set any number of items we would like, let's move on and see some of the interesting things we can do with sequence types. And the first of that is the ability to address or access individual elements or objects inside of a sequence. So let's see. Let's look at A. Currently we have 3 elements in A. That will work great for this example. In order to address the individual elements, we can use open and closing brackets, and those allow us to give an index. The index is based on the number of elements in your sequence and is 0-based, meaning that the first element is 0, the second is 1, and the third is 2, and so on. So if we were to look at element 0, that would be a 1. And even more interesting, since we're looking directly at that object, we're not looking at a tuple anymore, we're looking at that actual value. So if we looked at the type of A sub 0, that's an integer. So we're looking at that one integer value. As a matter of fact, to take this even further, let me very briefly redefine A as that list where we had tested multiple types, such as an integer, a float, and a string. So let's rerun type A0, still an int. Let's look at other ones. So let's say type A1, that's the floating value, and type element 2. And there's cat. So if we run type of element 2, that is indeed a string. So once again, the idea here is very simple, just the ability to address individual elements by an index. Now, looking at these individual elements, you might be thinking, well, this gives an easy way of updating data within a sequence. We can't do that yet because we're looking at a tuple, and a tuple is in fact immutable. It cannot be changed. To give an example of that, we could take A sub 0, which is 1. If we try to set that to 5, we get an error. Tuple object does not support item assignment. It is immutable. It cannot be changed. So, very good for storing an initial block, or excuse me, a tuple is very good for storing an initial block of data, but it cannot be changed in the future. So once it's been created, you either have to live with it or completely recreate it. Now, moving on from here, let's take a look at some more interesting things that can be done with indexing. We've seen that we have a 0-based index that allows us to access all of our elements. We also have the ability to do negative indexing. Now first let's think of why we would want to do this. Let's say we had run into a scenario where we wish to get the last element of a sequence regardless of how long it is. Because of course we know we could do A2, that gives us that last value of cat. But what if we wanted to be able to run a calculation and that would always give the last element regardless of where it was at? Well, if you think about it, we know how to find where the last element is. Length of A, that's 3. Can we address A sub 3? No, we can't because that's 0-based, so that falls off the end. However, we could do 3 minus 1. That would give us the last element. Of course, knowing how we got 3, we could replace that with length of A, and that gives us our last element. So now we could do something like set A equal to a smaller sequence, just 1 and 2, and rerun our sequence, and it's adaptable to any given size. Now, what I want to point out here is the fact that one doesn't have to go through all of this work. In some other programming languages, And this is what you have to do. When you don't have the concept of negative indexing, it's up to you to figure out what that last element is before you go in and specify it. In Python, you're allowed to index relative to the end of a sequence, and you do so using a negative index. That means you could use a sub -1, and that gives you 1 from basically the last element, 1 from the very end. Or -2 will give you 2 from the very end. So going back to the example of 3 elements, that is 1, 2.25, and cat.
And just so that no one's confused with what you said, it actually, the -1 gives you the 1 at the very end.
Exactly. So it's almost like in reference to the length, because it's seeing the same when we used length -1, we're using that same -1.
Right.
So it's going to be used almost like a shorthand of that statement.
Mm-hmm.
So once again, a -1. Now that we have 3 elements, it gives the last one, cat, or second from the end, or third from the end, or so on.
Very nice.
So very simple, but very handy to know that it's there so that you don't go out of your way doing additional programming for a feature which is already given in the language itself. All right, moving on from here, let's take a quick look at slice notation. So we'll take indexing even another step further, and I'm going to very briefly draw this or write this out on the whiteboard just so I can explain it before we go in and demonstrate it. The idea of having slice notation is the ability to pull a range out of a sequence. So what we're going to do here is we're going to have a syntax of, we'll use A as our variable. We could almost say sequence, but we've been using A for all the other examples. We'll use brackets to indicate that we're addressing some internal part of it. And the way the syntax works is we have a numeric value for the beginning or from, then a colon followed by 2, the ending condition. And the idea here is that you could say from element 0 to 2 would give you a subsequence. So this expression is actually going to return another sequence, but that sequence will be a subset of the one it was run from. This is, once again, very handy as you can do more complex operations, range operations, in a single line. Now, one last thing to note is the fact that the from element is inclusive and the to element is exclusive, meaning you are going to get whatever is placed here, and you're going to get 1 before whatever you place here. So, taking a closer look at that, let's set up a scenario with more values so we can get a better idea of how this range is working. Let's set A equal to a series of strings so that we can have a nice sequence of letters. We'll have A followed by B, followed by C, D, and E. So we have 5 different values. So looking at A, there are our 5 elements. Now, let's take a look at grabbing a slice of those into a subsequence. Let's look at what is the sequence A from element 1 to element 3. If we run this, we only get B and C. Well, once again, what was A1? A1 is B, and it is inclusive. So we can see that B was indeed the very first thing in our subsequence. And what was A3? A3 was over here. It was D. But what did we get? We only got B and C. Once again, the last, or the to operand was exclusive, so we go 1 before it. But with this in mind, we're now free to grab whatever range we would like. So we could start at the very beginning and run up to 3. We get A, B, and C. We can extend our range to 4, get A, B, C, and D, and so on. So this is grabbing a completely new sequence. It is indeed a tuple, as you can see indicated by the parentheses. And once again, just very handy for grabbing sub-ranges. Now, one other thing that's interesting to note is the fact that you can omit either the, or both the 2 and 4 parts of the notation. That means, let's say we wanted to come up with a scenario where we wanted from the beginning of the string until a specific point. We can omit the from portion, drop in the colon, and then drop our end. So going back to the original of ending at 3, we could say beginning to 3. That gives us A, B, and C. We can do the opposite, which is to specify the beginning and not the end. And that means from element 3 to the end, whatever that might be. So this returns just D and E. D being 0, 1, 2, 3. 3 is where D starts, and we run up into the end wherever that may be, D and E. Once again, this is very handy when you might be doing operations on sequences of variable length and want your code to be able to adapt to the different lengths. And of course, where this comes in handy is if you ever need to omit the first, just the first or the last element of something, of a sequence. You could say A1 to the end omits the first character, and A:(-1). And this is interesting here, because take a look at what we're doing. We're actually using negative indexing in conjunction with slice notation. So what is this going to do? Well, looking at the beginning, we're going to start at the beginning, A, and we're going to go up to 1 from the end. What is 1 from the end? That's going to be E, but it's exclusive, so we're dropping 1 back, and we'll omit the E. So we'll have A through D. So there we see A, B, C, and D. So once again, just giving these out as pointers to just things to think about as you're working in code and deciding, well, I need to drop the first part of a sequence or the last part of a sequence. These are very easy shorthand ways of doing this. But that, I believe, is going to take care of everything we need to look at as far as indexing is concerned. From here I want to move on and show one more thing, one more operator that is used in conjunction with sequences that can save you a bit of time, and that is the in operator. In will return true or false depending on whether or not the operand was found within the sequence in question. Again, this can save you time from manually having to look through things element by element. If you want to know whether or not a certain sequence contains something, you can use the in operator. Before we give a demonstration of that, let me set our A tuple back to the original 1, 2.25, and cat value. I like doing this simply because it gives a lot of very different values. So there we have all of our 3 values. What if we wanted to know whether or not the word cat was stored in this sequence without having to look at it element by element? Well, we could simply say whatever we're looking for, our operand, cat in A. If we run this operation, the result is true. Cat was indeed in A. If we look at another word or value, maybe dog, is dog in A? False. Dog is not anywhere in the sequence. Now, of course, you will generally use this or see this used in conjunction with more complex constructs like if statements. So you would actually see this as if cat in A, we would move on and do something such as print anything along the lines of yes, cat is in A. Let me say yes, cat is indeed in A. So that's how it would be used in context of an if statement. Well, once again, just pointing this out so that you don't run off and write code to look at elements individually when that functionality is built in using the in operator. Alright, so now we've seen a handful of things dealing with sequences. Now let's move on and look at another type of sequence altogether. Let's look at lists. First, the idea of a list is that it is a mutable sequence. It is changeable. Unlike a tuple, with a list we can go in and change the individual elements. We can even add and remove elements to an existing list. But to begin with, let's take a look at the syntax that is required to define a list. I'm going to drop down a few extra lines in our interpreter just to give a good separation. So, how do we go about defining a list? Well, we use syntax that is similar to a tuple, only we use square brackets instead of parentheses to specify the list. So, reusing the variable a, we could define it as opening square bracket and then give some elements, say 1, 2, and 3. Now, if we look at a, it is shown back to us with square brackets indicating that it is indeed a list, or if we like, we could check the type of A at this point and see that, yes, it is indeed a list. Alright, now that it's a list, let me also show, as we had done with tuple, we had shown a few special cases where we would need a sequence with 0 elements, 1 elements, or more. To cover the same thing here with lists, if we need an empty or 0 element list, we can simply use empty, open, closing square brackets. That gives A as empty. We could even check the length of A and see that yes, we do indeed have 0 elements. If we need only 1 element, we don't need to specify a trailing comma like we do with tuples. Since lists absolutely require the use of brackets, there's no way to get away with doing something like 1, 2. If we did that, that would be a tuple. We have to use square brackets in order to define a list. And with that in mind, we can safely put one by itself without a comma and get an actual list back out of it. Even checking with type, we can see that, yes, even though we didn't have a comma, we do have a list. The idea here is that bracket is not used for things like expression evaluation, like parentheses are used for. Since it is a dedicated marker here, we don't need to use the trailing comma. And of course, if we want to define a list with multiple elements in it, we simply use comma and specify as many elements as we would like. And let me set this back to 1, 2, and 3. Now, let's get into some of the interesting stuff with lists. Once again, the fact that they are changeable. That means we can not only look at element 0 of our list, which is 1, we can also change element or assign to an element. So we could say a sub 0 is equal to 5. Now again, this did not work with the tuple because it said that the tuple was not did not allow assignment. But look what happened here. A sub 0 equals 5. That worked. There was no error. If we look at A, we see that we now contain 5, 2, and 3. So we are free to change the elements of a list to our heart's content. As a matter of fact, we can even change how many things are in a list without having to recreate it. Let's take a quick look at the append and remove members of a list object. We can take an existing list, such as A, and we can append additional items to it. So we can say a.append and then specify whatever object we'd like added. Let's append the number 5 to it. And then look at A again. Now we have 5, 2, 3, and 5 again. And let's test the nature of putting different types of things into a list. Let's put the word cat in there, once again, just to make sure that we have the similar functionality to any other type of sequence or any other type of tuple. If we look at this, we can see that, yes, just like a tuple, we can put different types of objects into a list. So that's all well and good for adding things to it. Let's take a look at removing. We also have a remove member as part of the list, so a.remove. And let's remove the number 5. So we simply say, all right, well, what do we want taken out of the list? Well, 5. Now, what's interesting here is look at what we've got. We've actually got multiple occurrences of 5. So what's going to happen? Well, what this will do is it will remove the first value found, and only the first. The moment it finds an instance of 5 to remove, that's it. It doesn't remove any additional instances. So if we simply said a.remove 5 and looked at A, we took out that first instance of 5 and left the second one. That means if we wanted to remove all of them, we would have to run until we no longer had that value within it. So if we run remove 5 a second time, that gets rid of the second instance of 5. If we run it a third time, we actually get an error. If remove does not find the element you gave it, it does indeed throw an exception. So you will want to be careful when using remove, and you may want to use it in conjunction with the in operator to first make sure that there is an instance of that within the list before you attempt to remove it. Now, one last thing to take a look at is knowing that remove works on, 1, having to already know what you're removing, and 2, it works from the beginning on. What if you wanted more control over how things were taken out of a list? What if you knew right off the bat that I just want to take the last thing off the list? I don't want to worry about if there's multiple instances. I just know that for some reason I have found the index of the item I am interested in, and I want that one specifically to go away. Well, we can actually revisit the delete function in order to accomplish this. We can actually delete individual things out of a list by index. So using delete, we can say delete A and then give an index. Let's see, 0, 1, 2. Let's give the last one, so 2 for the cat. So A sub 2. And also be careful using delete, because if we use delete with A by itself, we could wipe the entire list out. But if we specify only delete A sub 2 and then look at A, we've taken out cat without having to worry about anything. In this case, we don't have to worry about what the object's type is, where it's at. We just have to make sure that it is within bounds, meaning we don't reference an index that is outside of the list. Another reason to show this is if you are familiar with other programming languages, very often you might have something that is a remove at functionality, so a remove function that takes in an index instead of an actual element. And by using deletion with an index, you can get that same style of functionality, the idea of deleting elements by index instead of by value. But having looked at delete, really that's all the specifics that I wanted to show for list. Everything else that we've seen in sequences up until now applies. All of the various forms of indexing, negative indexing, and slice notation also apply to lists. So just keep that in mind as you work with them. What we've done by taking a look at the mutability, the changeability, and the changeable nature of lists. Now, one last sequence type I wanted to look at was string. Let's revisit strings with some of our sequence abilities in mind. Let's make a string called text, and let's set it to the word hello. Now, of course, if we look at text, it is just the string hello, and if we look at its type, we are indeed looking at a string type, but a string is considered a sequence inside of Python. That means that we can look at text sub-0 and get that specific letter out. But keep this in mind, if we try to set a value to it, let's try to change the H to something else like a Q. We cannot, oh, I put the wrong quotes on that. Let me put both single quotes. We see that the string is immutable, just like a tuple. That is, it cannot be changed. You have to completely discard and recreate a string, and if you want a different one. So keep in mind, a lot of the tuple style rules apply here in that it is immutable. Now, knowing this though, we can still do a lot of interesting stuff because we have our full indexing abilities with the string. That means we could do things like, actually let me look at a slightly different version. Let's say we had our text equal to hello with a trailing comma. Let's say we had parsed input from some file. So text has a known character. Now let's say we wanted to very quickly go about stripping the end off. Well, if we remember from looking at our slice notation, we can grab everything up into the very end. We had used a blank beginning and -1 ending on slice notation to omit the last element. Let's apply that here with our text. Let's say text from the beginning to one character from the end. Omit the last character. If we do that, we get just the string hello. So of course we could go even further back and trim however many characters back we want. We could go all the way back to -4 and get just HE. So any type of range indexing we want to do is applicable to strings. This can be very helpful when parsing and otherwise working with string data. And really with that, that brings us to the end of this video. Once again, we were taking a look at sequence types within Python. We looked at tuples, which are immutable sequences. We took a look at lists, which are mutable or changeable sequences. And we took a look at the fact that a string is considered a sequence type, and therefore we can do indexing operations on it. We just have to keep in mind that strings are immutable. They are not changeable. So with that, that is going to bring this lesson to a close.